always going to be a problem. But, so today's lecture is going to be a little more computer sciencey than the rest. But since numerical analysis is about studying error, this is one of the most significant sources of error. And what leads to pretty much the differences between, or one of the main differences between numerical linear algebra and regular linear algebra. Because we have to take into account the fact that it's the computer that is doing all the real work in matrix computations. Okay. So what we have to contend with is that almost every arithmetic operation performed by a computer is erroneous. Okay, and the reason for that is because there is fixed, therefore limited, storage for numbers. So what that means is that most real numbers cannot be represented exactly. So there's, so for instance, numbers like integers up to a certain magnitude can be represented exactly, but and then certain decimals can too. But something like 1/3, if it has an infinitely repeating decimal expansion, or pi, or square root of 2, irrational numbers, we have to settle for an approximation. So certain numbers, the moment you input them into the computer and they're stored, there's already some error. And then those flawed numbers are used in other computations, and error can accumulate. So all kinds of things can go wrong. Okay. So what I'm going to do is discuss what are called floating point numbers. So this is the way that numbers are typically represented on a computer, and in particular the IEEE double precision floating point number system, which is one that computers typically use. Okay. So first this is annoying. Define floating point number system in general, and then we'll specialize to the IEEE case. Okay. So here we have a lot of terminology to introduce. So the floating point number x has this form. X is plus or minus m beta to the e. So I need to define all these things. Where m is called the Mantissa, essentially where the significant digits of the number go. And it's going to be similar to scientific notation, especially if this value, beta, which is called a base, especially if that's equal to 10. We could use whatever base greater than 1 for beta. And for computers, we're interested in beta equal 2. And then we have E is the exponent. Now, the form that the Mantissa has is a sum of powers of a base that are less than or equal to 0. So it might be a good idea intuitively to think of base beta as being equal to 10. So it's like, so the DJ here would be your decimal digits to the right of the, right before decimal point for j equals 0, and right after decimal point for j greater than 0. And then E would be your power of 10. Now, any floating point number system is defined in terms of certain key parameters. So one of the parameters is the base, beta. And the other parameters of interest, E is less than or equal to, there's certain bounds on the exponent that are referred to as L and U. And U is going to be positive, L will definitely be negative because we want to be able to have both positive and negative powers of a base. And then the other very important parameter, this value P. P is called the precision. So P is the number of significant digits that you have in whatever base you're using. Okay. I'm referring to E as the exponent. Some sources refer to it as the characteristic. Not really sure why. That's a really vague word to use in this case. Okay. Now, why we call it a floating point number is, I'll explain over here, is if the magnitude of the number changes, so if E changes, the Mantissa M does not. So whatever base we're using, if we multiply or divide by the base, that's just going to change the exponent. So multiplying would increase it and dividing would decrease it. And M remains the same. So you can think of the point, or decimal point, if you will, that's base 10, moving around within the Mantissa. If you were to have like the number written, not the Mantissa, but just X, so if you have the number written out in full. Okay. Now, so you can think of the decimal point floating to account for the exponent changing. Okay. Now, let's see. Now for computers, beta is going to be equal to 2. Interestingly enough, though, I read somewhere that a long time ago, the Russians actually worked with a computer, developed a computer that used base 3, but I guess it didn't really work out for them because it hasn't taken hold. So people try to change things back then. So
the third one refers to what?
I don't know. I don't know any details about it, but it's like, wow, that's really weird. Yeah, because you figure, 2 makes so much sense because 0 for off, 1 for on. And so what? Kinda on?
On and off?
Yeah. It's yeah, it's a little strange. Yeah, I should try to find out more about that. And maybe it didn't work out like because maybe something went wrong electrically, they burned the place down. Well, it reminds me of like how supposedly, you know, if a light switch is stuck between its on and off position or something, that I guess that could be like a that's kind of risky electrically. And so when I was little, my mom would always make sure like to tap the light switch to make sure it was really off, because she was like, "Oh, it's start a fire" or something like that.
Off.
Yeah. So really off. Yeah. And so then one time we're on a family trip and we arrived at our hotel and half a hotel is burned down. And the hotel's still up and running, you know, the other half, but yeah, it's just like total disaster area. So then my older brother, his infinite wisdom, says, well, I guess someone forgot to tap the light switch. Okay.
Is that true about the lights? Like,
That's what,
in that movie?
apparently, or it could be a wise tale, I have no idea. But. Okay. So here's some floating point systems of interest. So IEEE. Alright. So there is single precision and then there's double precision. So the precision, single or double, comes from how much storage there is for a floating point number. So single precision, you use 4 bytes, which amounts to 32 bits. So to describe how the bits are used, so we have 1 bit for the sign, so 0 for positive and 1 for negative. And then there are 8 bits used for the exponents. And then the remaining 23 bits are used for the Mantissa. And then for double precision, you have 8 bytes, so 64 bits. So you still just need 1 sign bit, so then everything else can be used for larger range of exponents and more significant binary digits. So 1 bit for sign, 11 bits for the exponents, and then 52 for the Mantissa. It's a breakdown there. Yeah, we didn't really feel the need to go that much further in terms of allowable magnitudes, and so most of the extra space is used for more precision. Okay, so if I write down the 4 central parameters for a floating point system, we have base beta, precision p, the smallest exponent L, and the largest exponent U. Now the base for both of these is 2, it's all binary. And then for the precision, you would think that it's simply the number of bits allocated for the Mantissa, but for reasons that I'll explain later, it's actually 1 greater than that. So 24 bits here, and then 53 the binary digits for double precision. Now for the exponents, if we have 8 bits here, so that can be used to represent a number between, so from 0, like if all the bits are 0, and actually, let's check my notation here. Or maybe I don't really name this. Okay. Because the exponent has to allow be positive or negative. So what you can do is you can use this to represent numbers between, like, well, so 2 to the 8th is 256. There's 256 possibilities. So you go from minus 27 up to 128. And similarly for double precision, 11 bits can be used. So 2 to the 11th is 2048. So you can use represent values from minus 1023 up to 1024. But it turns out you can't actually use all of those values. So almost all of them. So for single precision, we can actually go from minus 126 up to 127. And then from minus 1022 to 1024. And no, to 1023 rather. It's one less in both directions. And I'll explain later, the other values that are left out have certain special meanings, and I'll come to that in a little bit. Okay, so these are the essential parameters that describe these two particular floating point systems. And if you're using MATLAB, it's just going to use double precision. So by default, any computations are going to be using it.
Is there like a case where single precision would be preferred over double? Because like the way it looks right now, you would prefer to use double precision for almost any computation. Everything.
So a valid reason to use single precision is less storage, less data you're moving around, and that matters.
Like a faster, faster computation or something.
Well, because yeah, that's part of it. The actual arithmetic will be faster because the circuit is doing less work. Also, if you can imagine, one thing that's kind of overlooked, even, and I admit I kind of overlooked that in a class like this. When I'm thinking in terms of how efficient an algorithm is, I'm always focusing on the arithmetic because in the old days, where computers did not have as much memory and it didn't have like multiple processors and so forth, the time for the arithmetic really was the dominant amount of time. Not so much anymore because you have multi-processors and just the time to move a large matrix from main memory to cache memory and so forth, that starts to become more significant. And so if you can, if you don't really care about having this greater precision and you want to cut the time in half to move your matrix around, then that's good too. Now that we have multiple processors, that's even more of a concern. Just data communication is a big deal. Some computers offer extended precision, so even more storage than this. But that's not as common, and it'd be kind of like the ultimate cop-out for numerical analysis. Like, oh well, if my algorithm is not good enough the way it is, then I'll just get more precision, and everything will work just fine. If it's too sensitive around out there, usually you need to modify the algorithm some other way to work on whatever system you have.
So are we ever, like if we're using MATLAB, are we ever gonna, is there a way to change the way they, like what precision what type of precision?
Like from the MATLAB prompt, I'm actually not aware of it. I think it kind of roped into that. On the other hand, if you wrote C++ code that could, that you could set up to be called from MATLAB, then within that you can use whatever precision you want. So so what happens is in C++, there are different data types. The type is float for single precision, and we just call it double for double precision. Yeah. In fact, one popular book, Numerical Recipes in C, the author really prefers to use float for everything. And okay, whatever, it's on your high horse. But your less accurate horse. So.
So it is safe to say that like the more accurate your precision, or the You know, like if you go to the extent, then the slower.
Yeah, it does slow things down. Yeah. Okay. Now, okay, I'm going to do some examples involving representing floating point numbers using, whoops. Two different bases. So first base 10 and then base 2. Okay. So let x be minus 117. So if you're using a floating point system with base 10, in a way you represent it is x is equal to minus, your Mantissa is 1.17. I should mention, in the Mantissa you have these digits. The leading digit, d0, it corresponds to the base to the 0 power. That must not be 0. Because otherwise you're kind of wasting a digit. So your leading digit has to be non-zero. So in this case, this is your D0, D1, and then D2. So however much precision you have in your floating point system, these are the only 3 digits that are needed to represent this number. And then your base is 10, and then your exponent is 2. All right. On the other hand, to represent the same real number in base 2, x would be minus 1 point, we only have zeros and ones now, 110101 times 2 to the 6. So 6 is your exponent, and now you need 7 digits all told to represent the to handle the Mantissa. So if I were to convert this into a decimal, so 1.110101 is interpreted as, so the first digit times 2 to the 0 plus the second digit 2 to the minus 1 plus third digit minus 2 and so forth. And end up going all the way up to 2 to the minus 6. Okay. So then, if you were to write these out as fractions, you have 1 plus a half plus a fourth, and you skip this one, and then plus a 16th, plus 1 over 64. And if you were to do the whole common denominator thing, you would get 117 over 64. So that's 117 over 2 to the 6. But then you multiply by 2 to the 6, and you get 117. Okay. So of course, you're going to need more digits to represent a given number in binary than a decimal. But you have a lot of digits, especially if you're using double precision. Okay. Any questions about representation of these numbers? Okay. Now, some important properties of floating point systems. So, underflow and overflow. This has to deal with what magnitudes of numbers you're able to represent in your system. So the underflow level now that is the smallest representable positive number in that your precision and range of exponents will allow. And so what it's equal to is the smallest mantissa you can have times your base raised to the L power, where L is your smallest allowable exponent. Now, the question of what is the smallest mantissa, it's a little murky because it depends on whether your floating point numbers are normalized or not. So I should mention when I said that your leading digit is non-zero, that means the floating point number is normalized. If you choose not to normalize, so I'll give you choices. So m min is equal to 1 if normalized. So I made, or if I turn back for a second to correct this on the board. This does not always apply in every single situation. So when floating point numbers are normalized, then the leading digit in your mantissa is not allowed to be 0. So that's really good to mention here. And for the most part, like in IEEE, numbers are normalized. So this is the general case. But I want to point out an exception. Okay. So if not normalized, and the leading digit is allowed to be 0, but you can have all the digits of your mantissa equal to 0, except for the very last digit that is, so that would be your base raised to the minus p plus 1 power. Because if you see where I wrote down the form of a mantissa early on, your powers in the base started from 0 all the way up to minus quantity p minus 1. Okay, that's the wrong page. Okay. Okay. Got it. Okay, so therefore, the smallest allowable numbers either beta to the L if normalized, and beta to the L minus p plus 1 if not normalized. Okay. For example, in IEEE floating point, numbers are for most part normalized unless L is equal to the smallest possible value, minus 1022. In that case, IEEE switches to non-normalized to allow you to represent more very tiny numbers. So it's because of this and not normalizing at this point that underflow, I forgot the abbreviation for this, UFL, underflow level, is equal to 2 to the minus 1022 minus p, which is 53, plus 1. So that's going to be 2 to the minus 1074. And I think I have MATLAB open. Yes, I do. So what I'm going to do is I'm going to just type that into MATLAB and see what happens. So give you an idea, because 2 to the minus 1074. I want to see what it gives me. Okay. So that is in decimal, a little easier to relate to. That's roughly 5 times 10 to the minus 324. So that's a really badass small number. But now, if I type 2 to the minus 1075, it just says 0. So underflow is not a big deal. I mean, if you have a number that is too small to represent in your system, so smaller than that, it's fine for MATLAB or not really the software, it's not software, the hardware, to just declare it to be 0, and then computation can proceed just fine because it's already tiny anyway. Now, if you're in a situation where you're dividing by that number, then underflow could be a problem. But underflow is not really the major concern. It's the other one, overflow, that is a more significant. Okay, now, is there anything I want to mention about one reason why it's a good idea to not normalize is, so what happens is, okay, I'll write this separately over here. I should say denormalize numbers. In IEEE. So what happens is, this is triggered when the exponent bits are all 0. Okay. Because what happens is, the 8 or 11 exponent bits, so I'll limit myself to double precision just for concreteness, but so the exponent bits, the way it's interpreted is, if you're treated as an unsigned number, they can represent any number from 0 up to 2047. And then what you do is you subtract 1023. And that gives you values between minus 1023 and positive 1024. But like I said, you're not actually allowed to use all of those values for actual exponents. So, so the bits equals 0 corresponds to exponent equaling minus 1023. So then what happens is, that is interpreted as switching to denormalized numbers. Therefore, your Mantissa, like in the case of this smallest possible number, all the Mantissa bits are also 0, except for one of them. But one of the benefits of using denormalized numbers in a situation like this is, if all 64 bits in double precision are equal to 0, then the value is actually interpreted as 0. That's why denormalizing is important, because if you are normalizing numbers, so in my notes, I have a section on underflow and overflow, and then I talk about normalization. I'm kind of conflating the two, but it's really when you talk about underflow is when normalization becomes interesting. So normalized numbers, your leading digit is not allowed to be 0. So, what is the digit if we're in binary?
Like 1.
Yeah, 1's the only choice. Because now, unlike decimal, where you say, okay, the leading digit can't be 0, it could be 1 through 9. But binary, so in that case, if you know what the digit is, why store it? why waste that storage on a digit that you know what the value is going to be? That's why the precision is 53, not 52. So the extra bit comes from that, but it only applies to normalized numbers. If you're denormalizing, you give that bit up because now you have 52 bits and it can be anything. Okay, so that's an important aspect of these kind of numbers. So, and the thing is, if you decide that you're only going to have normalized numbers, denormalization is not allowed, then that means your mantissa can never be 0. The smallest mantissa that's allowed is 1. And then to represent a really small number, you could have a very negative exponent. You cannot represent 0 in such a system. So now, by denormalizing, you can. And it's a representation that makes sense. Just set all the bits equal to 0. So in both the mantissa and the exponent. So it turns out you actually have 2 ways to represent 0. What's the other way? You can have all the bits 0, but what's another way to represent 0 where you're still having denormalized numbers, but what other bit is allowed to be a non-zero bit?
A non-zero bit?
Yeah. Well, there's only 3 kinds of bits. Look at the picture I drew earlier.
Wait, the sign?
Sign bit. Yeah, you could have 0 and minus 0. That's still equal to 0. Yeah, so instead of having no zeros, if you only normalize, you actually have 2 of them. Okay. Now, okay. So if you ever know enough about underflow, you talk about overflow. So for overflow, alright, that's a little easier to work with. So that is beta to the u, so the largest allowable exponent, times beta minus beta to the minus p plus 1. And a way to see where this comes from, so u is the largest allowable exponent. This is the largest allowable mantissa. Now, in decimal, this would be the equivalent of 9.99999, as many 9s as you can have. Because what we're doing is you're basically 10 minus the smallest mantissa you can have, which is 0.0001. So 10 minus 0.001 is 9.99999. So the largest mantissa in binary would be 1.1111. All the mantissa digits equal to 1. So this is roughly beta to the u plus 1. Now u in IEEE double decision floating point is 1023. So presumably I cannot represent 2 to the 1024. In fact, if I go ahead and try that in MATLAB, let's see what happens. 2 raised to the 1024. Yeah, it says inf for infinity. So I've gone just a little too far. If I do 2 to the 1023 times 2 minus 2 raised to the minus 52. Ah, it gave me a number. Okay, so so I evaluated this for the parameters I gave earlier for U and P. So in IEEE double precision, the number is roughly 1.8 times 10 to the 308 power. Okay, so pretty dang big. Chances are you wouldn't need that in practical applications, but never know, you're covered. Okay. Well, by contrast, if I were to instead use the parameters for single precision, so the largest possible exponent, I had it written down earlier, but I erased it. I think it's like 127. Actually, can I see? Oh, yeah, 127. Okay. 27 times minus 23. All right, so the largest single precision is only in magnitude of 10 to the 38th power. Yeah, but again, still not likely to come across that in a practical computation. Okay, now that I'm, dang, I might actually fall behind. So now I need to talk about an extremely important topic, and that is rounding. Okay. So here are methods of rounding. The idea is you have a number that cannot be represented. So you have to come with some approximation to that number with the bits that you have. So the way you do that is there's chopping, which is also called rounding to zero. So for positive numbers, essentially, you're just always rounding down. It's something that, in my opinion, cruel teachers do to students. Like if they have an 89.5, they give them a B. So, yeah. And I know some faculty who do that. I'm not aware of any in this department, but okay, I think that'd be really more offensive. I mean, if someone's an English professor, like, they might not get it, but.
You missed that lesson.
What?
So they must have missed that lesson.
Yeah. And then there's just plain old rounding, or what we normally intuitively think is rounding, so rounding to the nearest. Okay. So if I nearest would be closest in absolute value. And then, but the thing is, that requires some sort of tie-breaking rule. So for instance, if it's 89.5 exactly, do you round up or you round down? The convention that I learned in school was to round up. But that's not the tie-breaking rule that is used here. The tiebreaker that is generally used is called round to even. So you round in such a way that the last digit of your number is even. So for example, 88.5 gets rounded to 88 rather than 89, whereas 87.5 also gets rounded to 88. And that's to remove bias, so in rounding. So numbers that land on a tie are equally likely to be rounded up or rounded down. Okay. Now, so notation that's important is FL of x is equal to the, okay, actually, let's check my definitions here. Yeah. So that refers to the machine number representation of x. Okay. In whatever floating point system you have. So you take your real x is allowed to be any real number, that at least within the allowable magnitudes. So after you do your chopping or rounding or whatever, and you have your approximation that is representable in your floating point system, that's FL of x. So this quantity, float of x minus x divided by x, assuming x is non-zero. Okay, so this is bounded by this number u, and that actually has many names. It's called a unit round-off, also called machine precision. So it's basically the maximum relative error that you can get in a number by rounding. Okay, so another way to think of it intuitively is that FL of 1 plus u is considered greater than 1 in the floating point system, but x is, or 1 plus epsilon is equal to 1 for any positive epsilon that is less than u. So u is the smallest positive number that you can add to 1 and still get something in your floating point system that's considered greater than 1. Okay. Now, as for what is the value of u, it depends. So when you're chopping, u is your base to the 1 minus p power. So in IEEE, it'd be 2 to the minus 52. Rounding gains you an extra digit of precision, so it's beta to the minus p. So it should be 2 to the minus 53. So I'm going to check that. So I do 1 plus 2 raised to the minus 53. Okay, that gave me exactly 1. Whereas if I get if I choose anything the tiniest bit larger than that, then I get something that's labeled as greater than 1. Okay, so MATLAB has a command called EPS, and it gives the value 2 to the minus 52, so the chopping value. But in terms of actually trying to add stuff, so u is slightly greater than 2 to the minus 53, which is 1.1 times 10 to the minus 16. So that's the amount of relative error, roughly, that you're incurring just by representing a number. But that's pretty good, nice and small. Yeah. Okay.
So is that an E like a different, is that an epsilon?
That's an epsilon.
Epsilon, okay.
Yeah. Yeah, so 2 to the minus 53 does not work, and I think that's why MATLAB identifies u as not 2 to the minus 53, but 2 to the minus 52. But
Is this the same u from when we represent like when we first used it to like the exponent, like if e is between.
oh
Is that
no,
the
no, no.
same?
This is okay. This is a lowercase u.
Okay.
Yeah, and I've had this bold in the notes. Yeah. Yeah, so I guess unfortunate choice of letter. Okay. Now for floating point arithmetic, certain issues that can come up, and see if I can do these in time. Okay. Well, now that I think about it, if I take 2 to the minus 53, yeah, because my negative powers of 2, when it's normalized, are like 2 to the 0, all the way, and then all the way up to, so I'm representing 2 to the minus 1 times 2 to, all the way up to 2 to the minus 52. So I could have a mantissa of 1.00001 where it's 2 to the minus 52, and that's greater than 1. But if I go one digit more, then it's gone off the edge. Okay. So that's something I'm going to have to look into a little bit. But for instance, okay. But evidently, I can take numbers that are larger than 2 to the minus, smaller than 2 to the minus 52, still add them to 1 and get something greater than 1. So it's a little bit of a mystery right now. Okay. Okay. Now, so here's some issues with floating point arithmetic. That what happens is, okay. You don't follow the laws of arithmetic exactly because of the error. In particular, well, I'll mention associativity. So you don't expect exact associativity to hold. Presumably commutativity would. Okay. Now, another problem is digits can be lost, if you will. Like for instance, if x plus y could turn out to be some of the floating point representation of that, could just turn out to be x if y is less than x, an absolute value, times the unit round off. So if y is so small compared to x, adding it literally won't make a dent. So that's something to be aware of. And it's for this reason, if you're adding a list of numbers, start with the smallest. So if you can sort them, so that way that information from adding those small numbers won't be lost. If you add them from the largest on down, you might as well stop early, depending on what the magnitudes are. Okay, and then finally, the biggest issue of all, and hopefully I can do it justice in time, is catastrophic cancellation. And I'll illustrate with a decimal example. So here I have two numbers I'm subtracting that are nearly equal. these numbers, they agree all the way until the last 3 digits. So I have 12 digits represented. So I go ahead and subtract. And I get 50. So now I only have 2 digits that I can use to represent my answer. I've just given away 10 digits of precision. So my difference, my result, is much less accurate than either of the numbers I subtracted. So this can cause problems with something as simple as a quadratic formula. So for example, here's a polynomial, x squared plus 10,000 x plus 1. And I use 4-digit rounding arithmetic. Actually, there are MATLAB functions, just to remember off the top of my head, to simulate rounding to a certain precision that's good for illustrating things like this. So what happens is, if you use this quadratic formula of 4-digit rounding, you get the roots. All right, so we're solving this equation. 0 and minus 10,000. But the thing is, if you plug in x equals 0 in there, you get 1 equals 0. So that's a little bit off. So if you use 7-digit rounding, then all of this is with the quadratic formula, as we know it. Then you get roots that are minus 0.0001, and then and then the other root is minus 9999.999. And that's so now you're getting some satisfactory roots. And the reason why is in your quadratic formula, if b is much larger than so if b squared overwhelms 4ac in magnitude, then you basically have minus b plus or minus something very close to b. One of those is same sign, addition, that's fine. If the other one's subtraction, it's going to go badly on you. So here's what you do. Do some algebraic rearranging. Multiply and divide by the conjugate of this. So the other quadratic formula, the one I never teach, is minus 2c over b minus plus b squared minus 4ac. So you could do that instead. So actually what you do is use both. So whichever one you use here, if it has the same sign operation, and this one has the same sign operation, will give you the 2 roots. So that's how computers actually do quadratic formula. They just use the 2 safe formulas. All right. Now, one of the problems with first homework deals with various floating point arithmetic issues. And I'm amazed that I actually got to that in time. And I don't think I really even glossed over any major points. But I want to explain why it's literally called catastrophic cancellation. It's a quite an interesting story, and I'll still finish on time. So, okay. This happened during the 1991 Persian Gulf War. So the idea was you have this Iraqi Scud missile that is meant to be intercepted by our Patriot missiles. Okay. they'd have to gauge the trajectory of the scud. So we're tracking the scud on radar and estimating its velocity. So its velocity is difference in position minus difference in time. And so then they could solve a simple ordinary differential equation to get an idea of where it's headed and then intercept it. And for the most part, this worked well. But on one occasion, the interception missed. The Scud got through, and 28 American troops were killed. So naturally, there's a government investigation, and whoever did the investigation seemed to know a little bit of numerical analysis, and figured out what went wrong. What happened was, whatever software is doing this, it's subtracting certain values of time, where the T1 and T2 is the amount of time since tracking began. So when these values are pretty small, the subtraction is just fine. But you leave this running for hours, days, weeks. Not that the war lasted very long, but still. These numbers, T1 and T2, got large, but the difference between them is still small. So cancellation happens if the absolute value of a result is much less than the two numbers you're subtracting. So at some point this would happen as you leave your code running, because T1 and T2 themselves are always increasing. So what happens is this subtraction turned out to be terribly inaccurate, thus throwing off the velocity, thus throwing off the trajectory of a Patriot, causing it to miss. So their solution was to restart the tracking equipment every 8 hours. So that way, that kept the size of these values, T1 and T2, in check. There'd still be some error, but they deemed it an acceptable level of error. And there were no further incidents. So by bounding the error, they solved the problem. And you can look this up, like all the documents from investigation and so forth, when we talk about this. Maybe not using the same terminology that I use, but still. So that's why it's literally catastrophic cancellation, and that's why numerical analysis has some nice, significant real-world relevance. And if only they had practiced it sooner when designing this software in the first place.
But I mean, restarting may cause other problems. They couldn't even,
Well, okay. For instance, if they fired a Scud while they were restarting, then that would be a problem. So, yeah. I guess there's always a risk, but at least it's something that helped. So, or I guess it was a simple solution at the time.
Okay, so it was just a simple solution at the time.
Yeah.
The main solution is something else.
I guess so. Yeah. Like for instance, in your code, just instead of saying time since booting up, just like have a code reset these time values to 0, as long as there's no current missile activity, and that also would work. But I don't know what their hardware was. Besides, this is 1991. Windows didn't exist yet, or the Windows 95 didn't. I think Windows itself did, but yeah. Because you're yeah. Well, I'm guessing we didn't have MATLAB out in the field. So.
I wonder what they do now.
What?
I wonder what they use now.
Yeah, good question.
Do you know what they were using?
I don't remember. I'm guessing.
Pretty basic.
Yeah, because this is discussed in certain numerical analysis textbooks, and I found documents online. It's like, oh wow, interesting. That's where I found out about their resolution. Yeah. Okay, so that's floating point arithmetic for you. That will cause you fits throughout the semester, or cause me fits because I have to explain how certain numerical algebra techniques are designed to avoid this kind of situation. Okay.